All right. So today kind of kicks off what will end up being a little bit of a big discussion and will carry over into next week. We're going to introduce what's called thermodynamics. All right. Thermodynamics has kind of a very straightforward goal. All right, so thermodynamics. This is the study of energy in a chemical process. All right. So which is, obviously a very important goal in chemistry is to study how energy plays a role. Energy is something that is very mysterious. We'll talk about it a little bit more in depth, but one of the reasons why is because it shows itself up in a bunch of different ways. You've talked about it in your physics class, I'm sure. Talk about it in the chemistry class. All right. The other thing to keep in mind about thermodynamics as we go through here is this is really, really old. All right. The foundation of thermodynamics is sort of one of the earliest kind of studies of chemistry. Talking about like late 1700s, 1800s kind of logic here, okay? So it was very important. It's a fundamental thing that we've just continued to build off of these days. All that to say they weren't full of it back then. They were really onto something, and we've just kind of expanded upon it. But you'll see here when we go through, there's some formalisms that you're like, really? Why did they even bother to say that, right? And it's because this is some of the earliest bit of chemistry work integrating energy that has occurred, okay? So, again, energy, kind of a weird thing. You've talked about it in your physics class. One of the things that makes it so weird is it shows itself in multiple ways. All right, so let's talk about chemistry in physics. Or, I'm sorry, energy in physics, where you would have heard this before. All right, there was this kind of energy called kinetic energy. And this is the energy that an object has due to its motion. All right, and then there's also what's called potential energy. And that is the energy that an object has due to its position in space. Okay, and both of these are energies, so they'd be measured in units of what? Joules, right? So these are both just energies. They're both forms of energy, but they're two completely different things. You kind of think about them in two different categories in your mind. All right, and importantly, we can convert from one to the other, right? So if an object has potential energy, we can convert that energy into kinetic energy. A very simple example would be like this eraser here, right? If I hold it up above the floor, it has potential energy because of its distance from the floor. When I let go, that potential energy is converted into kinetic energy as it travels through space, right? So both of these, two different forms of energy measured in the same set of units. It's just we think about them differently, and importantly, we can convert from one to the other. But in chemistry, we're not really talking about objects like baseballs or marbles like we are in a physics class. We're talking about atoms. All right, so we kind of have analogous forms of talking about energy here. So chemistry. All right, instead of kinetic energy, we have what's called thermal energy. This is the energy that a chemical system has due to its temperature. All right, and this is really just the same sort of idea as kinetic energy. It turns out that temperature arises because of the motion of atoms. So unless you are at the coldest temperature possible, absolute zero, you have your atoms or molecules in your system moving around, and that motion is what we perceive to be temperature. All right, we also kind of have an analogy to potential energy, what's called chemical energy. This is the energy of a molecule that is stored in its chemical bonds. And just like with our eraser at the front of the room, we converted its potential energy into kinetic energy. Likewise, we can convert our chemical energy into thermal energy and vice versa. Right? So these are two different forms of energy measured in the same thing. So kind of the weird thing about energy is from the universe's standpoint, it's all the exact same. But from us, our standpoint and the way we perceive it, it's very different. All right, so we kind of think about it in these different categories. Okay, so step one, we've kind of already talked about energy, but one thing that we are going to formalize now that we've really introduced it is the idea of these different units for energy. And in chemistry, you kind of see two that come up very often. We have the joule with the capital J. This is kind of like the fundamental unit of energy as physicists can consider it. So this is really popular in physics, which, why in there? All right. There's also the calorie. It's really important that you write this calorie with a lowercase c. I'll talk about why in a second. The abbreviation for that is cal. And this is the unit that's preferred by the biologists. And since chemistry is kind of in the middle of biology and physics, you'll see both of these come up. Typically, a particular field will kind of prefer one over the other. But of course, just like any set of units, we can convert between the two of them. All right, if we look on our constants page and we go down to our units of energy, right, we see that 1 calorie is actually defined as 4.184 joules. Okay, but what's that where have we seen that 4.184 number before? Does anybody remember? The specific heat. It's also the specific heat of water. Well, guess what? They do this kind of a lot, where they pick a relevant quantity and define something based on that. So yes, a calorie is defined as the specific heat of water, right? That same 4.184 joules that we've seen before. Cool. All right. There's also another context where you probably heard of calorie first, and that is a capital C calorie, otherwise known as a food calorie. And that has the abbreviation capital C calorie. This is used for food. Okay. And that capital C calorie is defined as 1 kilocal. All right, so when you look on the back of a package of food, it tells you how many calories there are in that food. It's telling you how much energy there is available from that particular source of food. It's scaled to be not just a regular calorie, but a kilocalorie. All right, cool. So let's do a conversion here. We got some food that has 150 capital C calories per serving. And you're going to take a second and tell me how many kilojoules of energy there are in, we'll make it just joules. Boom. Joules of energy there are per serving in that particular food item. Okay, and just to be clear, that number that we saw before was that one small C calorie was equal to 4.184 joules exactly. All right, so that capital C calorie is equivalent to 1 kilocalorie. And 1 kilocalorie is equal to 1,000 calories. And then I'm going to use my conversion factor, which tells me that 1 calorie is that 4.184 joules. Punch that into my calculator. And we get a big number here, 627,600. We look at our units here. That capital C calorie cancels out. That kcal cancels out, lowercase calorie cancels out, and we're left with units of joules. All right, and then finally, how many sig figs? Importantly, this definition here, again, it's a definition, so it's exact. Our metric prefixes are always exact. And a joule is, or rather a calorie is defined as exactly 4.184 joules. So we only have the amount of sig figs that we started with, which were those two. So I got 630,000 joules of energy from that 150 food calories per serving. Cool. Okay, so again, our discussion on thermodynamics is centered around energy and chemistry, right? Cool. So now we're going to define this quantity here called the internal energy. We're going to use this symbol U here. Okay? Internal energy is quite simply the amount of energy in a chemical system. So what do I mean by a chemical system? Again, thermodynamics is a very formalized kind of study here, right? So this is just a fancy way of saying whatever chemical reaction or chemical thing that you're studying, right? If you mix two solutions together and you have a precipitation reaction, your chemical system is that beaker, right? When we did that reaction where we dissolved that wire in the fume hood in that acid, that was our chemical system, was that reaction that was going on there, right? So this is just a fancy way of saying what you're studying in chemistry. Okay? And what you're going to see is, like, we don't really ever care too much about the actual value of U. What we care about are things that change that energy, right? So now we're going to talk about delta U here. And what does that delta mean? Change, okay? So delta U is equal to Q plus W. This is kind of a fundamental equation here in thermodynamics. So let's talk about this, all right? Again, the delta U, we just mean a change in internal energy. This Q we've seen before here. What did we use for Q? What did we use that variable Q for? A specific type of energy. Heat, right? Thermal energy. And the other one is one that we haven't talked about in chemistry class. You actually don't really talk about it too much in chemistry class, but you do talk about it a lot in physics. Does anybody have a guess what that W stands for? Work. Absolutely. Okay. All right. So what this fancy equation here is saying is that we can change the internal energy of a chemical system one of two ways. Either through heat or through work. All right. One of these two is going to be way more important than the other, we're going to see. All right. It turns out that most chemical systems, you get to kind of ignore the work component. We're going to talk about the work component here in a second. We're going to see it kind of narrowly applies. So we're going to spend a great amount of time focused on that heat component going into next week. All right? But for now, let's take a second and talk about work. Okay? Again, let's talk about our physics definition of work. All right, where you would have heard this talked about before in physics, this is the force, actually, well, yes, but it's the transfer of energy by a force acting on an object as it is displaced. All right, so when I take this and I move it across the table there, all right, I've used force to displace that object, to move it from one position to the other. I put in work to do that. And that is this quantifiable thing that you can do in physics class. You quantify that exact amount, all right? But there's one sort of key word here that we want to pay attention to, our key phrase. And the idea that in physics and in chemistry, this is a way to transfer energy. All right, but again, we're not talking about objects in chemistry the same way that we are in physics class. All right, so we're going to prefer our more chemistry definition here, which is a very specific type of work. All right, this is what's called pressure volume work. Okay, and so pressure volume work is in a chemical system. It's a chemical system that changes volume against an external pressure. Actually, we're going to say against or with, depending on the direction, an external pressure. All right, so what do I mean by that? We're going to take a simple system here. We're going to take a cylinder. All right, we're going to outfit that cylinder with this movable piston here. All right, so this is just a piston that can move up and down. Whoops. And we're going to fill it with some gas. So we have our gas in here at this specific volume. And pushing down on this piston is this external pressure. All right, the pressure of the gas inside must be equal to the pressure of the outside, otherwise our piston would move here. If we were to expand that gas, all right, such that now our gas is at a larger volume, and we have moved our piston up. So we have this new volume here. We're going to call this V2. There would have been work performed. Specifically, that gas inside performed work on that external pressure by moving that cylinder. All right? This process here would coincide with a transfer of energy. This reaction in particular in this kind of system is exactly what is propelling your car down the road if you have a combustion engine vehicle. What happens is your car sprays some gas into this cylinder. It then combusts it so that that gas expands, moving that piston up. And through the magic of engines and transmissions, I'm not a mechanic, all right? But that motion gets translated into the motion of your wheels, right? Going down the road, okay? And that, again, is what we call work. There was this transfer of energy that occurred here. It's a quantifiable thing, right? So we can actually put a number on this here. So we're going to use this equation for our pressure volume work here. We'll just title this again. is equal to the negative external pressure times that change in volume. All right, so let's perform our calculation here. We're going to stick with our little piston system here, and we're going to say if the gas's volume changes from an initial volume of 1.5 liters to 12.7 liters, and this is against an external pressure of 1.25 atm. I want you to calculate the work in joules. All right, so I'm going to give you all a minute, see if you can't calculate the amount of work that was performed by our gigantic engine in this case, if that's our volumes. So work is equal to that negative external pressure times that change in volume. Remember, it's the final minus the initial. I'm going to be good and do my subtraction problem first, so I know how many sig figs there are in that difference. And when I multiply this together, I get my work is equal to negative 14. How many sig figs should there be? Our initial pressure has 3. And then we were good and we calculated our difference here. That also has 3. So I'm going to have to make this 14.0. But what are my units here? Liter atmosphere. I didn't cancel anything out, right? So my units here are still atm liters. So what the heck? All right. If we look on our constants page, believe it or not, pressure times volume, ATM liters, is indeed a unit of energy. All right, so just like all of our other units of energy we can convert, it turns out that 1 joule is 0.0098692 ATM, liter ATM liters. So in order to finish this problem, I'm going to take my negative 14.0 and I'm going to divide it by that 0.0098692. I get negative 1,418.555, 554, yeah, 555, fine. Doesn't matter, I'm going to stick with my 3 sig figs. All right, so my final answer here is that negative 1,420 joules of energy in this system here. And that sign is very important. Remember, we talked about our sign of our thermal energy. It really just tells you which direction it's going. We have the same sort of formalism here. All right, so we have some fancy terminology. Negative work means that the work is done by the system on the surroundings. And if it's positive work, we say that the work is done by the surroundings on the system. All right, and so now we have this same kind of terminology that we've heard before about system and all that jazz, right? This really formalized way of thinking about it here. Okay, so let's take our piston example again just to be clear. Our chemical system here is that gas. All right, that's what we're studying. That's what we saw expand and move that piston. So what then is the surroundings? It's literally everything else, right? So our surroundings, if we put a big old box, this piston is sitting in some room somewhere or underneath the hood of an engine, whatever it may be. Everything else is the surroundings. Right? Your surroundings are literally defined as everything but the system. All right, so then if we were to push this piston down, we would see that we would get a negative change in volume, which meant that it was the surroundings that was doing work on that gas by compressing it. All right, so again, depending on what, this is very similar to what we saw for Q. Depending on the sign of the delta T, we would get a different sign of Q. Same thing here if we look at this equation. Depending on the sign of that delta V, we're going to get a different sign for our work, and that just sort of has a different interpretation of what's being done here. Is the work being done by the system on the surroundings, i.e. that piston moving up, or is it being done by the surroundings on the system, i.e. we're compressing that gas? Cool. All right, and that pretty much concludes our discussion of work here, all right? Again, kind of very important for types of reactions, specifically like combustion reactions, which are used literally because of the work that they can generate, right? That's why we use combustion reactions. But aside from that, if a reaction doesn't sort of lead to this expansion of gases, and many reactions do not, that work term is irrelevant, right? Because you have to have a change in volume for there to be any sort of pressure volume work. So if, for example, we mix two solutions together and we have an acid-base reaction or we have a precipitation reaction, there's not any work that's going to be performed in those reactions. So then this part of it we don't care about, and then we're really focused on that thermal energy aspect, right? So that's what we're going to see is changes to our chemical system because of we're taking heat in, or we're adding heat or taking heat away. All right, cool. So we're going to talk about the laws of thermodynamics here. Okay. The laws of thermodynamics, they get their name laws because you probably have heard that everything in chemistry or in science is just a theory, and that's absolutely true, right? We're always trying to gather evidence. We don't really claim that anything is truth. However, we have certain theories that have stood the test of time so freaking much that we're like, all right, we're going to graduate you to a new status here. We're going to call you laws, which means that there's just nobody has found any sort of a flaw in these laws of thermodynamics yet. All right, they're about as close to truth as we can say here. So the first one is what's called the zeroth law. There's 4 of them. They start at 0. Our first one is the zeroth law of thermodynamics. All right, what is the zeroth law of thermodynamics? It says that if two chemical systems are in thermal equilibrium, with a third system, then they are also in thermal equilibrium with one another. All right, if we have two chemical systems and they're in thermal equilibrium with this third system, then they must be in thermal equilibrium with one another as well. All right, so then this kind of begs the question, what the heck do I mean by thermal equilibrium? By thermal equilibrium, I simply mean the same temperature. All right, so let's kind of diagram this out pictorially here. We're going to make 3 boxes. All right, we got 3 boxes. They're filled with gas. We're going to call these different chambers chamber A, B, and C. All right, so A and B are in thermal equilibrium. All right? Which is again of saying a fancy way of saying that the temperature of A is equal to the temperature of B. And I'm going to tell you that B and C are also in thermal equilibrium. Meaning that the temperature of B is the same as the temperature of C. So what can we say about the relative temperature of gas A and gas C? I guess I kind of gave it away right there. What's their relationship? They got to be the same. All right. So that's what the zeroth law of thermodynamics is telling us. If we have two systems like A and C that are that are in equilibrium with one another, they must also be in thermal equilibrium with themselves. Oh my gosh. If you have two chemical systems that are in thermal equilibrium with a third, they must also be in thermal equilibrium with one another. All right? And I hope that everybody, when they kind of think about it, looks at that and says, well, yeah, duh. All right? Cool. But again, you have to remember, like, when is this being established? Late 1700s, early 1800s. Guess what isn't everywhere? Thermometers, right? This is kind of the basis of this idea that temperature could be measured, something that was not really appreciated for a very long time. First of all, we're all living in a world where we see measurements everywhere. That was not the case, right? For a long time, there was a select few who were kind of educated enough to deal with numbers, period. And then the idea that, like, okay, you can measure from here to here. Sure, we can wrap our heads around that. But the idea that that temperature, that heat that we're feeling outside is something that could be reliably measured was not something that was appreciated at all, right? So this really fundamentally provided the basis of measuring something like temperature. Something that's so easy to do now that we kind of take for granted wasn't all that straightforward back in the day, okay? Cool. So now the other one that we're going to talk about. There are 4 of them. 2 of them we won't talk about until next semester because you have to learn about something called entropy, which is really weird, and we're going to kick the can on that to Chem1B. All right? So the next one that we're going to talk about is what's called the first law of thermodynamics. This is also called the conservation of energy principle. All right, and this is this idea that energy cannot be created or destroyed, only transferred. This might sound a little bit familiar because we've always talked about how matter cannot be created or destroyed, right? We use that principle to balance our chemical reactions. You have to have the same number of carbon atoms on the reactant side as the product side because none of them disappeared into thin air and you didn't create any new ones, right? So this is kind of an even more fundamental statement. Energy itself cannot be created or destroyed, only transferred. All right, and we're going to measure, we're going to talk a lot about these different transfers of energy. Cool, all right, and now we're going to put these first, we're going to put the zeroth and the first law of thermodynamics into practice here. All right, we're going to call these our thermal equilibrium discussion. All right, I am going to take a piece of metal here. Let's say it's aluminum. And I'm going to heat this thing up until it's glowing red hot. And then I'm going to take this beaker of water. And my water that I filled it up with, I just went to the tap and filled it up. So it's room temperature or relatively cold compared to that block of aluminum. All right, so what is going to happen when I take my beaker of water and I drop in that block of aluminum? What are we going to see? Or rather, what's going to happen at the chemical level here? Is my aluminum just going to stay a hot piece of aluminum and my water going to stay cold water? No. What we're going to see is a transfer of heat from the aluminum into the water until it reaches what's called thermal equilibrium, which is again just a fancy way of saying they reach the same temperature. All right, so when these two systems are brought into contact, there will be a transfer of thermal energy until they reach thermal equilibrium. All right, so we kind of have our zeroth law at play here, the idea that these two have reached this thermal equilibrium, which means that they're going to be the same temperature here, okay? But again, the way that they reach thermal equilibrium is through this transfer of heat, which is just another form of energy. All right, so let's say that Q aluminum, this is the heat lost by that aluminum block. And then if we have our Q water, this is the heat gained by the H2O. Right? According to our conservation of energy here, what must be the relationship between these two? If my aluminum lost 10 joules of energy, where did that 10 joules of energy go? Into the surrounding water bath. All right, now remember, if something loses thermal energy, it will have a negative sign. Whereas if something gains thermal energy, Q will have a positive sign. All right. So our first law of thermodynamics tells us that our Q aluminum plus our Q water has to equal 0. Okay, and again, this equation here is just a restatement of that first law because it's saying all energy lost by the aluminum must be absorbed by the water. Cool. All right, so we've talked about these specific heat equations that we can use to get these thermal energies here, right? If we have a mass and our specific heat of our substance, as well as a change in temperature, we can calculate that value of Q. All right, so let's just remember Q equals Hc times M times delta T. So if I wanted to calculate the Q of aluminum, what heat capacity would I use? I would go look it up for aluminum, and I would use the mass of aluminum, as well as the change in temperature of aluminum, and then I could calculate how much heat that aluminum lost, right? Likewise, if instead I wanted to know the Q of water, I would use the heat capacity of water, and the mass of water, and the change in temperature of water. Cool. All right, so let's see if we can put this, kind of combine our specific heat and our first law of thermodynamics to do the following problem. All right, we're going to take 50 grams of aluminum and we're going to heat it up to 120 degrees Celsius. We're going to place that aluminum in H2O at 23.5 degrees Celsius. At thermal equilibrium, the H2O has reached a temperature of 36.3 degrees Celsius. And what I want to know is what is the mass of that water? Took this 50-gram block of aluminum and we heated it up to a to a temperature of 120.0 degrees Celsius. We then dropped it into this cup of water that was 23.5 degrees Celsius. We let this system reach thermal equilibrium, which was a temperature of 36.3, and we want to know how much water was in that cup. All right? And so again, we're going to need to use our specific heat and our first law in order to solve this problem. So I want everybody to take a second, take a stab at it, see if you can't figure out what to do here. I will say that we're going to need a few heat capacities, so I'm going to put those up here. The heat capacity of aluminum is 0.900, and the heat capacity of water is that 4.184. Sorry, let me rearrange here. Cool. All right, cool. So everybody take a second, see if you can't solve this problem here. right, so if we look at our heat capacity equation, we see that we have all the information that we need to calculate the amount of heat that was lost by the aluminum. We have the heat capacity of aluminum, the mass of aluminum, and the delta T of aluminum. Okay, so plugging this in here, this is that 0.900 joules per gram degrees Celsius. Started out with 50 grams of aluminum. And now for my delta T, I need final minus initial. What is the final temperature of that aluminum block? 36.3, but in the problem it says that that was the temperature of the water. But it was in thermal equilibrium with the aluminum, right? Which means that they're going to be that same temperature. Now, remember, read this problem carefully. The 36.3 is the final temperature, not the initial temperature. The initial temperature was very hot, 120 degrees, right? So my 36.3 minus 120.0 degrees Celsius. And I want to be good and do my subtraction problem first. So that's negative 83.7 degrees Celsius. And again, that sign is really important. So punching that all into my calculator here, my Q aluminum is going to be negative 3766.5. Okay, if I look here at my units, grams cancel out, degrees Celsius cancels out, so I'm left with units of joules. Okay? Let's look at our specific heat equation again, but this time for water. Okay. We can definitely look up the heat capacity for water. And if we read our problem carefully, we have enough information to calculate our delta T of water. We have an initial and a final temperature. And this problem is asking me for what? The mass. So what I want is this variable right here. Right, but I got too many missing variables unless I can figure out what that Q of water is. And again, this is where we're going to use our conservation of energy, our first law of thermodynamics, which says that the Q of aluminum plus the Q of H2O has to equal 0. Right, that's what our first law of thermodynamics tells us. So if the Q aluminum is negative 3,766.5, what's going to be the Q water? Positive 3,766.5. I guess I need to be good. I had 3 sig figs on that. Keep that marked. There's a 3.7. Cool. So then I'm just going to plug in everything else. I know that my Q is the 3,766.5 joules. This is equal to that 4.184 joules per gram degrees Celsius. And what I don't know is my mass. But I know that my my final temperature was that 36.3, and my initial temperature was 23.5. So then to get M all by itself, I'm going to have to divide both sides by that heat capacity times delta T. So I'm going to have to divide. It's going to cancel out over here. Right, so I'm going to divide, and I guess we can be good and do our temperature first. Do we lose a sig fig? I don't think so. No. 12.8 degrees Celsius. and we get a mass of water of 70.3293. I guess I'll put in my values here so we can make sure of our units. Degrees Celsius cancel out, joules cancel out, and I'm left with 1 over grams, which is the same thing as grams. And finally, I'm going to round my answer to 3 significant figures. So my mass of water was 70.3 grams. Okay? So what we did for these thermal equilibrium problems here is we had to utilize both our calorimetry equation, our specific heat equation that we learned about last week, and then also what we learned about today, our first law of thermodynamics, which says that if any bit of thermal energy is lost by one object, it has to be gained by the object that it is now in thermal equilibrium with. Cool. All right, we're going to end it there a little bit early because I'm going to give you time to view your exams.